Hello students, in the last lecture video we have discussed about the definition of culvert, types of culvert, different parts of culvert, differences between a bridge and a culvert, and we have also in detail discussed about the step-by-step estimation of 4 items of RCC slab culvert. So in today's lecture video we shall discuss about the remaining items. I'm Soumya Sahu, lecturer in Civil Engineering at SKTV Government Polytechnic, Rourkela, and this video lecture is prepared for 5th semester Diploma Civil Engineering students. The load acting on the slab is high at the center on bottom, so the bottom will experience a sagging moment whereas the support will experience hogging moment. So the bottom of the slab at center and the top of the slab at support will have high tension at the same time. So you will observe a higher value of deflection in shorter span, whereas a low value of deflection in the longer span. The main purpose of providing a main reinforcement bar is to transfer the bending moment developed at the bottom of the slab to the beam, and it is provided in the shorter span. So that is exactly why main reinforcement bars are provided at the bottom of the slab and in the shorter span, whereas the distribution bars are provided in order to resist the shear stress and the cracks which are developed in the longer span. And these distribution bars are provided at the top of the main reinforcement and in a perpendicular direction to the main reinforcement bar. You can see the main reinforcements are provided in the shorter span, whereas the distribution rods are provided on the top of the main reinforcement in the longer span. So when and why crank bars are provided? Crank bars are provided to take the steel to the top at support, because generally bottom steel are not required at the support, because the bottom of the slab at center and the top of the slab at support experience high tension. So in order to compensate that tension, crank bars are provided. And why hooks are provided? Main reinforcements are provided with sufficient extension length considering the safety against bond failure, and this extension length is at least equal to the development length. But in case if it is less than the development length, then at that situation anchorages like hooks are provided. So next let's see what is bar bending schedule of a cranked bar. So the bar bending schedule, most commonly known as the BBS, is a comprehensive list of type, size, length, number and bending details of a bar in reinforcement diagram of a structure. In this figure you can see a standard hook. Here the distance from this point to this point it is 4d, where capital D is equals to the diameter of the bar. So length of one hook equals to 9 into capital D. See, this is 4d, this is plus D plus again 4d. So length of one hook is equals to total 9d. And what is the total length of the bar? Total length of the bar is equals to capital L plus 18d, where capital L is equals to the length of the beam or the slab minus the two end covers, and the total length of the bar equals to capital L plus 18d, because length of one hook is here 9d and another hook here is 9d. So L plus 18d. How the additional length for bent up bar is derived. Okay, in this cranked portion, this forms a triangle. See, this forms a triangular shape. So this becomes the hypotenuse, this becomes the perpendicular, and this becomes the base. So in order to find out the additional length for bent up, we have to subtract base from the hypotenuse. So how can we get the value of hypotenuse? See, here this angle is 45 degree and this is a right angle triangle. So sine 45 equals to P by H. If this vertical distance, we take it as small d, and the base also becomes small d. So sine 45 becomes, so sine 45 equals to P by H, that means d by H, and suppose this is H, so hypotenuse is equals to d divided by sine 45. So in order to get the additional length of the bent up bar, we have to subtract the base from the hypotenuse. So we have already derived the expression for hypotenuse, which is nothing but small d divided by sine 45 degree. So if we subtract this with the base, that is small d, we will have d divided by sine 45 degree minus d, which is equals to, if I take d common, then it is 1 divided by sine 45, sine 1 divided by sine 45 minus 1, which will be equals to 1.42 minus 1 into d, which is equals to 0.42 d. And for two bent up bars, this additional length will be 2 multiplied with 0.42 d, so that will be equals to 0.84 d. So with this background knowledge, we will go into the step-by-step estimation of the remaining items. So the next item is steel bars including bending in RCC work. So in order to find the quantity, we have to first calculate the number of steel bars used as main reinforcement bars. So in order to find this number, we have to first divide the entire length of the slab with the center to center spacing, and we have to add 1 with it to find out the total number of steel bars which is used as main straight bars. So the total length of the slab is 4.8 meter. From the plan it is very clear, because the slab is from here to here it is provided. So 4.8 is divided by 0.3, which is nothing but the center to center distance, plus 1. So we will have this as 17 number. So 17 number main straight bars with 30 centimeter center to center distance is provided. And so see again the figure here. In order to find out this length, we have to follow the BBS. So the length will be, first we have to take the length of the slab, that is from this point to this point. So this is 1.5 meter is from this side to this side, and either side it is 30 centimeter. So total length is 1.5 plus 0.6 equals to 2.1. So here 2.1 meter minus 2 side covers. We have to subtract 2 side covers. In slabs, usually 40 mm side covers are provided, plus 18 into D, where D is nothing but the diameter of the bar. So 2.1 meter minus 2 into 0.04 plus 18 into 20 into 10 to the power minus 3. So if we calculate this value, we will get this value as 2.38 meter. Okay, so let's quickly fill the table. So this length is 2.38 meter, and the breadth and height of main steel bars are very negligible, so we can neglect it. We can find out the quantity of main straight bars by multiplying the number of main straight bars with the length, that is 17 multiplied with 2.38. We can have it as 40.46 meter. Then next we have to find out the number of main bent up bars. Okay, in order to find out the number of main bent up bars, we have to divide the entire length of the slab with the center to center spacing. So 4.8 divided by 0.3, which is equals to 16. So 16 number of main bent up bars are provided, and the length of the bent up bar is calculated by adding the length of the main straight bar with the additional length of bent up. Since there are two number of bent ups are present, so length of main straight bar, that is 2.38 plus 0.42 into D into 2, which is equals to 2.38 plus 2 into 0.42D, 2.38 plus 0.84 into D, which is equal to 0.38 plus 0.16 equals to 2.54 meter. And the total quantity is obtained by multiplying 16 with 2.54, which is equals to 40.64 meter. And the total quantity, which is 40.46 plus 40.64 equals to 81.1 meter. So the total quantity of main reinforcement, which is to be expressed in kgs, can be found out by following the steps I'm going to say. So we have to multiply the area of the bar with the unit weight of the steel with the total quantity of length we have calculated. So first I'm going to write the area of the bar. So pi by 4 into d square, which is 20 mm. Since the unit is in millimeter, I'm going to convert it into meter, multiplied with unit weight of steel 7850 kg per meter cube, multiplied with total length, that is 81.1 meter. So we will get this value as 200.32 kgs. So next we have to calculate the quantity of distribution reinforcement as well as distribution reinforcement. So first, the distribution reinforcement is provided at the bottom at 25 centimeter center to center distance with 10 mm diameter bars. In order to find out its number, we have to divide the length of main straight bar with a center to center spacing, that is 0.25, and we are going to get this number as 9. And to find out its length, we have to first take the length of the slab and we have to subtract it with the end covers, two number of end covers, and then we have to add the total length of hook. So 4.8 minus 2 into 0.04 plus 2 into 2 into the length of standard hook, where the length of standard hook is equals to 9 into 0.01. Okay, so we are going to get this value as 4.9 meter. So if we multiply 9 with 4.9, the quantity will be 44.110 meter. And then next is distributing top bar. So distributing top bar, here the number of distributing top bar is generally half of the number of distributing bottom bar. So we have taken this number as 4 and the length is already calculated as 4.9, and if we multiply 4 with 4.9, we are going to get 19.6 meter, and the total quantity is 44.10 plus 19.60 is equals to 63.70 meter. And by following the procedure that I have mentioned earlier, we can easily calculate the weight of the steel required for distribution reinforcement, and the total quantity of steel is found out by adding the steel required for main reinforcement and the steel required for distribution reinforcement, which is 200.32 plus 39.49 kg equals to 239.81 kg. The next item is cement concrete used in wearing coat. Wearing coats are provided in order to protect the structural concrete over the road from the damage of traffic or from the damage of rainwater. You can clearly see there is only one number of wearing coat provided here. Here also 10 centimeter cement concrete wearing coat is provided. So its length is same as the length of roadway. So the length of wearing coat is 4 meter, and its width is going to be from, breadth is going to be from this point to this point. So its entire breadth is 2.3 meter, 1.5 plus 0.4 plus 0.4, which is equals to 2.3 meter, and its depth is 10 centimeter or 0.1 meter. So let's quickly fill the table. The number is 1, the length is 4 meter, the breadth is 2.3 meter, and the height is 0.1 meter, and I have already calculated the quantity. It is 0.92 cubic meter. The next item is cement pointing work. Pointing work is done for the finishing of joint mortar. Okay, so the first pointing work is done in the face wall from 10 centimeter below the ground level and up to the bottom of coping. It is done 10 centimeter below ground level. So from here the pointing work has begun up to where? To the bottom of coping, up to this point. So the total height will be how much? From this point to this point, this height is 0.5 plus 0.2 equals to 0.7. So 0.7 plus 1.3 which is equals to 2 meter and 10 centimeter below the ground level, so 2.1 meter. So the height is 2.1 meter and the length would be 4.7 meter from this point to this point. Okay, and the number will be 2 because the face wall from the front, we are seeing the front view, so we are seeing only one face over here. So on the back side there is another face, so there are 2 number of faces. So we are going to write here 2 number of faces. The length as 4.7 meter. The breadth as, there is no breadth. Pointing work, plastering work, these are expressed in square centimeter or square meter. And the height is 2.1 meter and this quantity is 19.74 square meter. Next, the inner side of parapet excluding the coping. So we have to do the pointing work on the inner side of parapet. We have to do the pointing work on the inner side of parapet, and the number would be 2 because here pointing work is to be done and here this side also pointing work is to be done. The length would be 4.7 meter. We have to find out the height. So from this point to this point the pointing work is done. So from this to this point this height is 0.5 plus 20 centimeter. Here to here the height is 20 centimeter. So 0.5 plus 0.2 equals to 0.7 and below that we are having here 10 centimeter height. So total 0.8 meter. So let's fill the table. The number is 2, length is 4.7 and the height is 0.8. So the quantity would be 7.52 square meter. Next, the pointing work is to be done in the coping. Okay, so here in the coping the pointing work is to be done. So there are 2 number of copings here and here. So the total length of the coping is 4.9 meter. Here the total length of coping is 4.9 meter and we have to find out its now we have to find out its breadth. How we will calculate this? See, this side pointing work will be done. This projection is 10 centimeter. This height is 10 centimeter. This breadth is 40 centimeter and this height is 10 centimeter. So 10 plus 40 plus 10 plus 10. So total breadth is 0.7 meter. So let's fill the table. Number is 2. Length is 4.9 meter. Breadth is 0.7 meter and the quantity is 6.86 square meter. Now the pointing work is to be done at the ends of parapet. So the pointing work is to be done at the ends of parapet. So here this side we are having one end, here we are having one end, and since this is a 2-dimensional figure, we cannot view the other 2 ends. Behind this there are also 2 number of ends of parapet. So there also the pointing work is to be done. Here first we have to do the pointing work for the 40 centimeter breadth parapet. So the breadth is 40 centimeter and the height for which pointing work is to be done is 20 centimeter. And for 30 centimeter breadth parapet, the height for which the pointing work is to be done excluding the coping is 60 minus 10 centimeter equals to 50 centimeter. So let's quickly fill the table. And so the number is 4. Here also the number is 4. The breadth is 0.4 and the height is 0.2. The quantity is 0.32 square meter. Here the breadth is 0.3 meter. The height is 0.5 meter and the quantity is 0.6 square meter. Next, the pointing work is to be done for the ends of coping. So there are 4 number of ends. Here the breadth at the end of coping is 40. So the breadth of the coping is 40 centimeter, and this side, this end pointing work is done, and this end the pointing work is done. So 10 plus 10 equals to 20 centimeter height. Okay, so I'm going to fill it as 4.4 breadth, height is 0.2 and this quantity is 0.32 square meter, and this total quantity would be 35.36 square meter. Now we have to deduct the rectangular opening. We have to deduct this rectangular opening and this triangular portion because we have calculated these items also while calculating the cement pointing work. So we have to deduct this rectangular opening and the triangular portion. So there are 2 number of rectangular openings, so number would be 2. The length of this rectangular opening is 1.5 meter and the height is 1 plus 0.3 equals to 1.3 meter. And for the triangular portion, the area would be half into base into altitude. So half into, here altitude is 1.3 meters, slope is given 1:1, so the base is also 1.3, so half into 1.3 into 1.3. So let's fill the table for rectangular opening, which is 2 in number. The length is 1.5 meter and the height is 1.3 meter and this quantity is 3.9 square meter, and this rectangular portion, this quantity is 1.69 square meter. Okay, so the total deduction would be 5.59 square meter and the net total will be 29.77 square meter. With this we have completed the detailed estimate of RCC Slab Culvert. From this chapter, the most probable 2 marks question that you may get is define culvert, state the difference between bridge and culvert, what is the purpose of providing wearing code, what is the purpose of curve, and what is the purpose of a parapet. So these are the expected 2 marks question that you may get in the examination. And from long question answer section, you might get questions like to prepare the detailed estimate of slab culvert for the following items, and the items would be mentioned like earthwork in excavation, cement concrete work in foundation, first class brick work. So you have to make the table and you have to enter all the data after analyzing the plan and sectional elevation. So thank you very much, students.